We are going to start seeing some circuits that are a little bit more complicated. These circuits might have multiple batteries, or they might have many different resistors in combination with batteries in a bunch of different branches. And the way that then we've been treating circuits by finding the equivalent resistance, finding the current, and then breaking it down into pieces is not going to be the easiest way for us in order to tackle some of these larger circuit analysis problems. So we are going to learn a couple of rules that will help us be able to better tackle these problems where we have circuits with many different components, multiple batteries and multiple resistors in the same circuit. These rules that we'll be referring to are called Kirchhoffs rules. They're named for the inventor, Gustav Kirchhoff, who lived in the mid to late 1800s. Imagine that we have a circuit that has many different branches or directions that current can choose to take. That current is running through the circuit, and maybe there's the circuit branches off into a couple of different branches, and then that current has to divide or split among those branches. And the way that we can deal with the current in that situation is by appealing to Kirchhoff's first rule, which is also called the junction rule. This rule, Kirchhoff's junction law, states that the total current coming into a junction must equal the total current leaving the junction. A junction is just a place where that current can separate. So for example, right here, we have a junction. We've got the currents that I'm going to call I1 over here coming into the junction, and then that current splits off into two directions. And the current coming out of that junction then is current 2 going this way and current 3 going that way. So if the total current into a junction must equal the total current leaving the junction, that means right here at this point where the current can split, the current coming into the junction I1 equals the sum of the current coming out of the junction, which would be the sum of the current through this branch, I2, plus the current through this branch over here, I3. This rule is a direct result of the conservation of charge, which is also the conservation of current. Imagine that current is like water flowing through a pipe. The same amount of material that comes into the pipe has to be the same amount of material that comes out of the pipe if that pipe splits off into different branches. And we can write this in equation form, and that says that the sum of all the currents coming into the junction equals the sum of all the currents coming out of the junction. And remember, we saw this Greek symbol last semester. This is a capital Greek letter sigma, which represents in this case the sum of stuff. So we might not necessarily have one branch of current coming into a junction. There might be two branches of current coming into a junction. So the sum of those currents at the junction coming in has to equal the sum of the current coming out. So that's our first rule, Kirchhoff's first rule, which we sometimes call the junction rule. Then we have Kirchhoff's second rule, also known as the loop rule. For any circuit, if we add all the potential differences around a loop formed by the circuit, then the sum of all those potentials must be 0. Okay, and so this statement right here can be written in equation form here. The sum of all the potentials around our loop must equal 0. Okay, so how do we apply that? Here we have a loop inside a larger circuit. Okay, so you can choose whichever direction you want that loop to go around inside your circuit. Here, they've started the loop right here, and then we're going around clockwise around the loop. So we add up all of the potential around the circuit. So we add up the potential across this element, plus the potential across this one, plus the potential across this one, plus the potential across this one as we go around the loop. And so the sum of all of those together must equal 0. But we haven't really said what these elements are. Maybe these elements are resistors, maybe these elements are batteries. There are different rules for the sign on which we give that potential, depending on the direction of current and whether we are looking at a resistor or a battery. So let's just look here at this schematic. We have a battery, and we've got the negative terminal and the positive terminal here. We have our loop. We're moving around our loop. We're going from the negative end to the positive terminal of our battery. We're coming around here, we're going through resistor 1 and then through resistor 2, and then we've ended our loop. So as we're traversing through the loop in our circuit, we gain potential. So this is a graph of the potential around our loop here. We're going to gain potential as we move through the battery. And then, so from A to B, we're gaining potential. And then we move from B to C, there's no element there, so our potential remains the same. And then here, when we go through C to D, we are going through that resistor in the direction of current. We are going to decrease our potential as we move through that resistor in the direction of current. And then as we move through the second resistor, we're going to decrease our potential even more as we move through that second resistor. And then we're going to come over here and end our loop. So we sum up all of the potential differences that we encounter as we go through the loop, and the sum of all of those has to equal 0 whenever we end our loop back where we started. So here we're moving through our battery in the direction of current from the negative to the positive terminal. We're increasing our potential. And then when we move through those resistors in the direction of current, we're decreasing our potential. So the sign that we would use when we're summing up all those potentials in our Kirchhoff loop, if we're traversing our Kirchhoff loop and we're moving from the negative terminal to the positive terminal of our battery, we call that a positive potential or an increase in potential. So V gets a positive sign when we do that. Now let's say that we're moving in our Kirchhoff loop in the direction of current, but we encounter a battery where we encounter the positive terminal first and then the negative terminal in the direction of current. So as we're moving through our Kirchhoff loop, let's say that this battery were flipped here, the negative terminal were up here and the positive terminal were down here, we would be decreasing our potential as we move through that battery. And so we would put a minus sign on the potential of this battery. Now, if we're traversing that Kirchhoff loop and we're moving through a resistor in the direction of current, we're going to decrease our potential. So when we move through this resistor here, we're decreasing our potential. You could put a voltmeter on either end of either side of this resistor and get the potential across it. But we also know that that potential is equal to the current times the resistance. And so we could write this potential as the current running through that resistor times its resistance. And if we're moving through that resistor in the direction of current, we're decreasing our potential. So the potential we would write as we move through this resistor is minus its potential drop from both sides, or minus the current running through it times the resistance. The opposite is true then. If we're traversing our Kirchhoff loop in the direction opposite that of current, and we move through our resistor, then we're going to increase our potential. So this chart is always helpful for me whenever I think about, am I going to put a positive sign or a negative sign on that potential as I traverse my Kirchhoff loop? We're going to apply these rules to do some circuit analysis with a circuit that has 2 batteries instead of 1.